Welcome to this session of our lecture series on superconducting resonators. This series is brought to you by the NYU Nanolab, the Laboratory for Quantum Materials and Devices. We would also like to give special thanks to the Nord Tech Hub and the Microelectronics Commons for making this lecture series possible. This short session focuses on deriving the Hamiltonian of an LC resonator. While it is not strictly necessary for working with superconducting resonators, we take a brief detour to introduce this concept because the Hamiltonian is often used to connect the classical and quantum simple harmonic oscillator. The quantum harmonic oscillator is central to understanding superconducting artificial atoms or qubits. By presenting this derivation, we hope to make your transition into studying superconducting artificial atoms smoother, should you choose to explore that path in the future. In this context, we have a single learning objective for this session: to derive the Hamiltonian of the LC resonator. The first step is to plot the energy of the resonator as a function of magnetic flux. We do this because, in the literature, the energy plots of quantum LC harmonic oscillators are usually presented in terms of magnetic flux. This convention also helps when transitioning to the concept of anharmonicity in artificial atoms. For us right now, it is simply a change of variables. Recall the energy versus inductor current plot from the previous session. Since the inductor current equals the magnetic flux divided by L, we find that the magnetic energy Wm is equal to the flux squared over 2L. In other words, the energy in the inductor depends quadratically on the flux. This means we can replace IL with phi on the horizontal axis of the energy plot without changing its meaning, since Wm remains a parabola. We then substitute the inductor current by the flux divided by L into the simple harmonic oscillator equation, as shown here. Our next step toward deriving the Hamiltonian of the LC resonator is to use an analogy with another simple harmonic oscillator, the mass spring system. The equation of motion for a mass attached to a spring is shown here, where m is the mass, x is its position, and k is the spring constant. Comparing the two systems side by side, we observe the following equivalencies. The magnetic flux phi corresponds to the position x, the capacitance C corresponds to the mass m, and 1 over the inductance L corresponds to the spring constant k. The energy of the mass spring system is the sum of potential energy, EP, and kinetic energy, EK, given by 1/2 kx squared and 1/2 m times the speed squared, respectively. In the LC oscillator, the energy in the inductor as a function of magnetic flux is 1/2 phi squared over L. Since phi corresponds to x, the inductor energy is analogous to the potential energy in the mass spring system. Similarly, the energy in the capacitor, expressed using the voltage V, which is the derivative of the inductor flux, is analogous to the kinetic energy in the mass spring system. It is important to note that if we had chosen the charge Q in the capacitor as the coordinate instead of flux, the energy in the capacitor would appear as potential-like, and the inductor energy as kinetic-like. The physical energies remain the same, only their mathematical form depends on the chosen generalized coordinate. We choose magnetic flux because it is commonly used in the literature to represent the LC quantum harmonic oscillator in superconducting quantum circuits, as shown in this graph. Having established the expressions for potential and kinetic energy, we can now write the Hamiltonian of a simple harmonic oscillator. As with some of the more complex concepts we have introduced in this series, a detailed discussion of Hamiltonian mechanics is beyond the scope of this lecture. Our goal here is simply to present the concept and highlight its significance. The Hamiltonian of a system is a function that represents its total energy. More importantly, it expresses this energy in terms of generalized coordinates and their corresponding generalized momenta. For the mass spring system, the Hamiltonian is the sum of the potential and kinetic energy written in terms of the position x and its momentum p, where p equals the mass m times its velocity. This gives the following equation. By analogy, we can derive the Hamiltonian of the LC oscillator. We established the equivalencies between position x and magnetic flux phi, and between mass m and capacitance c. Consequently, the product of mass and velocity in the mass spring system corresponds to the product of capacitance and voltage, which equals the charge Q in the capacitor. The Hamiltonian of the LC resonator is therefore the sum of two terms, the magnetic flux squared over 2 times the inductance L, and the charge squared over 2 times the capacitance C. This separation of energy into an inductor term and a capacitor term is a key concept for understanding the quantum harmonic oscillator and, ultimately, superconducting artificial atoms. This ends this light speed session. Thanks for watching and see you in the next one.